Welcome to this explainer. Look, if you've ever stared down industrial standards, you know they can feel like a total maze of dense tables, charts, and microscopic tolerances. Well, today we are breaking down the highly specific engineering requirements of API Specification 5L into a clear, navigable roadmap for pipeline integrity. We're going to uncover exactly what it takes for massive steel pipes to actually be deemed safe for the real world. To make sense of all this, we've organized our journey into 5 essential checkpoints: strength and physical testing, surface imperfections and defects, dimensions, mass and tolerances, weld seam requirements, and finally, inspection and documentation. Let's dive right in.
Starting with Section 1, Strength and Physical Testing.
When you dive into the massive testing tables in the standard, you'll see 2 critical parameters constantly weighed against each other: minimum yield strength, which is the exact point a material bends permanently, and tensile strength, the absolute maximum stress it can take before completely failing. Now, it's not just about hitting some huge number here. It's really the delicate relationship between these 2 metrics that dictates the pipeline's ultimate safety margin.
What's actually wild here is just how tight these windows are. Take grade L415 pipe, for example. The specification explicitly demands a yield strength somewhere between 415 and 565 megapascals. But it also requires a higher tensile strength starting at 520. Why? Well, it's to keep that crucial strength ratio strictly below 0.93. This built-in buffer basically guarantees that if a pipe gets overpressurized, it's going to stretch and bulge long before it catastrophically snaps.
But physical strength isn't just about pulling steel apart, right? It's also about bending it. When they put this steel through a rigorous guided bend test, 3.2 millimeters is your hard, non-negotiable limit. If there are any cracks or ruptures in the weld metal or the parent metal that exceed 3.2 millimeters in length, it actually doesn't even matter how deep they are. That piece is instantly rejected. Done. We see this exact same strict scaling in the CVN impact tests too. These tests measure how well the steel absorbs set-in energy to prevent brittle fractures. Notice how the absorbed energy requirements ramp up precisely depending on both the pipe grade and its specified outside diameter. Like, a standard pipe might need an average of 27 joules of energy absorption, but as the pipe gets wider, say over 12-19 millimeters in outside diameter, that requirement jumps all the way up to 54 joules. So the bigger the pipe, the more energy it absolutely has to be able to safely absorb.
All right, moving on to Section 2, Surface Imperfections and Defects.
Here is the ultimate question for literally any quality control inspector out in the field. How deep is too deep? I mean, when you're manufacturing thousands of feet of massive steel pipe, minor scrapes and abrasions are just bound to happen. But at what precise, microscopic measurement does an acceptable little scratch suddenly transform into a massive structural liability? Well, the specifications give us a crystal-clear triage process for issues like undercuts. Shallow cuts under 0.4 millimeters, okay, those automatically pass. But hit that mid-range between 0.4 and 0.8 millimeters, and inspectors have to start carefully measuring individual lengths against some really strict ratios. And anything beyond those limits, it's no longer just an imperfection, it is an absolute defect, and it requires immediate rejection. Another absolute limit you've got to memorize is 50 millimeters. During manufacturing, you can get localized points of intense heat or friction that create these hard spots on the steel. If any hard spot on the pipe is larger than 50 millimeters in any direction, and its hardness exceeds 35 HRC, boom, it's classified instantly as a defect. The standard simply does not mess around when it comes to localized brittleness. Inspectors also have to reject pipes showing laminations, which, if you aren't familiar, are basically internal separations in the steel, if those extend into the face or bevel over 6.4 millimeters. Same goes for a cold-formed dent with a sharp-bottomed gouge deeper than 3.2 millimeters. Out it goes. Fundamentally, any imperfection that eats into the minimum permissible wall thickness is an automatic failure. We're not just talking about cosmetic scratches here. These are things that compromise the structural integrity from the inside out. Which brings us to Section 3, Dimensions, Mass, and Tolerances. It's really not just about getting the wall thickness and diameter right. The straightness of a massive pipeline is strictly governed too. You can't exactly just eyeball a 40-foot pipe, right? The standard dictates that the maximum total deviation from a perfectly straight line over the entire length of the pipe is capped at a tiny 0.2% of that length. This is where that abstract math translates directly into the physical world. Inspectors will literally use a taut string or wire, running it all the way from one end of the pipe to the other just to measure the deviation gap in the middle. It's actually a surprisingly simple, almost ancient geometric trick, but it's being used to enforce a highly modern microscopic tolerance.
And let's look at the pipe ends for a second. For sections that actually need to be welded together, inspectors use a fixed square to ensure the end face is perfectly flush to the pipe body. That out-of-squareness gap is strictly capped at a maximum of 1.6 millimeters. I mean, if it's off by even 2 millimeters, that final weld just won't seat properly.
Next up is Section 4, Weld Seam Requirements.
When you're joining giant steel plates into a massive cylinder, obviously you've got to weld them shut. And making sure the internal and external weld beads align perfectly is absolutely crucial to preventing weak points. They define weld bead misalignment precisely as the distance between two parallel lines drawn across the internal and external fusion lines.
So to actually measure this in the field, inspectors have to find the midpoints of both the inner and outer weld beads, draw a line perpendicular to the pipe's tangent, and calculate the exact radial offset distance. This kind of complex geometric measurement is what ensures that structural forces flow evenly across the seam, rather than creating this deadly localized tearing force. The stakes here are just incredibly high, so as you guess, the tolerances are incredibly tight. Standard wall pipes up to 20 millimeters thick literally cannot exceed a 3 millimeter misalignment limit. Now, if the pipe wall is thicker than 20 millimeters, they do give you a slight allowance up to 4.0 millimeters. But adhering to these tiny numbers is really the only way to guarantee complete penetration and fusion of that weld. Finally, our last stop, Section 5, Inspection and Documentation.
Okay, so what's absolutely crucial to understand here is the sheer paperwork burden. For standard PSL1 pipe, the inspection certificate has to rigorously catalog a massive amount of data. We are talking specified dimensions, the exact chemical composition of the heat product, the tensile test results we talked about earlier, the specific hydrostatic test pressure applied, and the exact non-destructive inspection method used. It's basically an exhaustive resume for every single piece of steel. But if you're stepping up to the higher standard PSL2 pipe, which you typically see in more demanding environments, well, that checklist expands significantly. Manufacturers are forced to also certify the CVN impact results, detailed carbon equivalents for weldability, and drop weight tear test results. The manufacturer essentially has to prove, on paper, that this specific pipe can survive the harshest conditions out there without suffering a catastrophic brittle fracture. Which kind of leaves us with a provocative thought as we wrap up this explainer. We've looked at massive steel tubes, high-pressure tests, and microscopic tolerances today, but ultimately, the physical strength of that pipeline sitting in the ground is entirely dependent on the uncompromising strictness of the documentation that verifies it. If a single 4 millimeter misalignment goes unrecorded, the entire system could be at risk. So the real question is your paperwork as strong as your steel? Thanks for joining me on this journey through API 5L, and keep looking closely at those details.